Today's discussion will be on classification, but last time we saw linear methods for classification. Today we'll be looking at nonlinear methods. So the reference for today's discussion, Bishop's book, section 5.1 and 5.2. Chapter 5 is on neural networks, and 5.1 and 5.2 mostly deal with this neural networks for classification. Last time we saw some linear models. Today we'll be looking at nonlinear methods, primarily neural networks. Okay, so let's start with this one. So what is multi-class classification? In the last lecture, we looked at the classification problem where we are given different kinds of flowers, 3 kinds of flowers, and we have to identify one flower from it, means whether it is rose or lotus or jasmine, right? So out of many classes, one class is true. So we make a model, let's say our model is height and width, the input, let us call it as x vector, and then some hidden units, and then outputs. How many outputs should I keep? 1, 3, 6. Capital C. Okay, so I'm giving the example of when C is 3, rose versus lotus versus jasmine. So my C is 3 in this case. So yes, C or 3. Okay, so okay, I think I'll come back to this question after discussing this 2 slides, because you will see some interesting things happening here. Okay, so what is multi-class classification? You represent your output with 3 neurons. So if it is a rose, basically if you remember from last discussion, what was the rule which we used? That my class is Arc Max of HC. H is basically the output here, like H is equal to, let's say this is I0, I1, I2. So Hi2 is equal to Wi2, I1, Vi1 summation plus the bias. So let's say my V already includes the bias also. So summation over all I1. Right, my H is that linear mapping, and then my Y is, you remember last time we discussed this multi-class classification problem. So this kind of decision rule, or this kind of, it does not have any ambiguous regions. We discussed it in the last class. Okay, so that's why we are using this approach. Yc is equal to argmax of Hc, and Y is a one-hot vector. This is straight from previous class discussion. We looked at 1 versus all, 1 versus 1, and finally we decided upon this kind of a classifier where we just assign the maximum value, the argmax, to be the actual class. Now, in this case, this is a nonlinear system, right? So I cannot use least square estimation to find my explicit update rule, my optimal solution for W using analytical methods like just differentiate, put the derivative equal to 0, solve for W, and you get the best W, optimal W. That is not possible because this is a nonlinear system, nonlinear model. So there can be many nonlinearities here, like this layer can have nonlinearities, this layer already has a nonlinearity, this one, right? So what approach do we use to update the rules, update the weights? Backpropagation or gradient descent, right? So we use iterative methods to update my weights, to train my weights or to find the optimal set of weights. And then my requirement is that my nonlinearities should be differentiable, yes. And is Arc Max differentiable? Arc Max is not differentiable, right? Did we miss something? Okay. Sorry. Okay, fine. Yeah. So my Arc Max is not differentiable. So I have to find an alternative for Arc Max which is differentiable. You remember from last discussions, in the past we have seen step function, right? And which was not differentiable, and we converted it into a form which is differentiable. What was that form? Huh? What was it? Sigmoid function. Very good. So we converted it into a sigmoid function, sigma of x, which is differentiable. So we will do something similar here. We have to find a differentiable function which looks like Arc Max. So here is a candidate. This is the candidate. It's technically called a softmax function. Okay. So what it is, it looks something like this. So you have your HC, right? This is your HI1 or sorry HI2 or HC, because this I2 refers to the class, right? This refers to the class. So okay, HC. So let us say my answers are something like this. My H vector is something like this. Let's say 2.1, 0.3, 1.1. Okay, let's make it even smaller, 0.8 something, okay. What will be my y in this case? Can you calculate using this formula? What will be my y? Okay, you don't have your calculators. Mobile phones. Or should I do it? At least I can write the formula here. So it will be something like this. First calculate the denominator, because denominator is common for all. Denominator will be e to the power 2.1 plus e to the power 0.3 plus e to the power 0.8. So my y will be basically these values, e to the power 2.1 divided by denominator, means the whole thing divided by denominator, e to the power 0.3 divided by denominator, and e to the power 0.8 divided by the denominator. This will be my y. So ideally my answer should be 100, correct? Ideally it should be 100 if I use Arc Max. So with Arc Max my y should be equal to 100. But with softmax, what should be my y? You can calculate it. It will look something very similar to Arc Max, something very similar to 100, right? Okay. Anybody able to find out the answer? Huh? 0.7, 0.11, 0.18. Okay. This is something like Arc Max, right? The first element has the largest value, and other two elements have less value. So basically, if you want to make it closer to Arc Max, then you increase your h further, like the first entry or the h0, increase it further. Let's say make it 5 or 10, and then you will see your y will look almost like 100, very close to 100. Okay. Next.
These are increasing functions, so it doesn't really matter, right? If I take just the highest value.
Pardon? These are increasing functions. What is increasing function?
Suppose these three values we take, and e raised to x divided by a summation over e raised to x. This is going to be following the same fashion, right? 2.1 will lead to the highest value. 2.3 will lead to the lowest value.
Yes. So why are we using this increasing function? I could have used any increasing function.
Or not even.
Yeah, I could have simply used unity. Okay. Unit line then.
Yes,
Which means your y is simply equal to h0 upon h0 plus h1 plus h2. So okay, please tell me what is the problem with that solution? Who will tell the problem? Just let me write it down. I think this is a... Sorry. Okay. So let's say I have got another kind of y which is equal to h, okay, yc is hc upon summation hc dash, sum over all c dash. Huh? It can be? Why? Okay, so what is the solution? Make, like this? Okay, so let me go step by step. What is the problem with this solution? The problem with this solution is very simple. The problem is that my h belongs to real, right? So it can be positive or negative. It could be any value. So which means my denominator could be negative, denominator could be 0, or denominator could be positive as well. That is a problem. How do we get rid of that problem? This could be negative or 0, which is not good, right? Any other problem with this? Huh? Yeah. Yes. Yes, the function will be non-differentiable. If it is negative, you put some approximation to make it 0 or positive, then again it will be non-differentiable, right? And another point, okay, one thing is we want to make it all positive. So, okay, why can't I use simply... So basically one thing is clear, I have to use some function which is positive and which is continuous, right? Something like this. This is my x, this should be f of x. It should be positive, my f of x should be greater than 0, and it should be monotonously increasing, and it should be differentiable. Huh? I could take sigmoid. What is the problem with sigmoid then? But still it is monotonous, it is increasing, monotonously increasing, it is differentiable.
The values will be very close to each other.
Yes. So the problem is, if you see, this is 2.1 divided by 2.1 plus 0.8 plus 0.3. This is still very far from what is it called? Still very far from Arc Max. This is still very far from Arc Max. If I use sigmoidal of 2.1 divided by sigmoidal of 2.1 plus sigmoidal of 0.8 plus sigmoidal of 0.3. Even in this case, let us say sigmoidal of 2.1 is very close to 1. Sigmoidal of 2.1 is very close to 1. Sigmoidal of 0.8 is also very close to 1. Let us say we can ignore this. Okay, let us say this is close to 0.5. So the overall value, my y vector will look something like this. 1 upon 2.5, or let's say maybe 0. Okay, let's say this is 0.9 to make it a little smaller. 2.4. So it is 1 upon 2.4. The other value will be 0.9 upon 2.4, and the other one will be 0.5 upon 2.4. This is still very, very far from Arc Max, right? So the kind of pull which will be provided by this derivative, basically the derivative will be very small. If you find its derivative, it will be very small, so it won't be able to learn properly. So basically, if your error function is not very steep, if it is very shallow, right, you won't learn very fast. And because of noise and everything, it will be not learning at all. That is the problem. So, but what is the use of exponential function? That this exponential function makes it more steep. Exponential, so any differences are exaggerated by exponential function, but they are suppressed by the sigmoid function. Is this point clear? How do you know that? If the derivative is greater than 1, the differences are exaggerated. If derivative is less than 1, the differences are suppressed, right? And sigmoid function, the derivative is very small, so the differences are very much suppressed. But on the other hand, in the exponential function, derivative is very large, differences are further magnified. If something is 2.1 versus 0.8, the difference is 1.3. But if you take exponential, the difference between exponential will be much, much larger than simply 1.3. That is why it will very well resemble the Arc Max function. So just remember, anytime you want to exaggerate the differences, use an exponential function. And if you want to suppress the differences, you will use a sigmoid or logarithm. So logarithm also suppresses the differences. Okay. Okay. Now we have found out the nonlinear. Okay. So now we have found out the nonlinearity. Now, how do we train our classifier? So let's go back to the figure. So in this figure, we have found out my y, how the y will look like, right? I have obtained a y. My y vector is equal to softmax of h vector. Now, how do I train? What should be the error function? Can I use squared error function? Can I use squared error function? Okay, I will write squared error or mean squared error actually. Can I use mean squared error here? Raise your hands if yes. Yes, so Ashish. Huh? Okay, yes, you can use, why not? But why don't we use? We don't use because I think we discussed this point. The derivatives are very small. Maybe we'll discuss that point again. The mean squared error, it leads to poor learning. It's a quadratic function and the derivatives are not sufficient to pull your weights to the right value, right? So you need a stronger pull to 0 or 1. Mean squared error is very good for continuous thing, right? For any continuous approximation, which means regression problems. Mean squared error is good. But now in this case, you know your answers are discrete, either 0 or 1, ideally. So you want a very strong pull to these discrete values. So that's why we don't use mean squared error, but we have to use some stronger pulling error function. So one observation which can be made is that this y vector is it sums to 1, and it is every value is greater than 0, right? So it looks like a probability function, right? Because it sums to 1 and each value is greater than 0. And so also the target values. The sum of target values is also 1. Why? Because it is a one hot vector. Single entry is 1, everything else is 0. So what would you like to use? What error function you would like to use to compare two probability distributions? No. You read it here, that's why you are saying, but it's not the right answer. KL divergence, yes. You use KL divergence to compare two distributions. Actually, I am very well aware that we have not discussed probability theory, but we will do it after this is over. We'll go to probabilistic models and everything. So KL divergence is the one which we use, and you can call it categorical cross entropy, but what I find is that it can be interpreted as KL divergence too. So I have two distributions. One is the YC. So one is YC. I'm not able to use my pen. Yeah, so one is YC, which, let's say if we have three classes, it will look something like this, right? It's a 2.1, 0.8, 0.3, and I have my TC, which, let's say this is YC. Right? I want to compare these two distributions. So how do I do that? I can use KL divergence, which is something like this, or I can use cross entropy, which is something like this. TC, in this case, what will be the error function? So for C is equal to 0, how will it look like? TC is 1 and YC is, it was 0.7 something, right? 0.7, 0.1, 0.18. Let's say 0.2. So what is my YC? 0.7 plus, for C equal to 1, what is my TC? 0. For C equal to 2, what is my TC? 0. So my cross entropy error, with a negative sign, it will look something like this. So it is log of 0.7, right? And I want to minimize my error. When will the error be minimum? When will the error be minimum? When YC, when 0.7 becomes 1 basically, right? Because log of 1 is 0. Log of anything less than 1, let me draw the log function. It is, something like this, asymptotically falling, right? This is log of x and this is x, right? So I want to make it, because we are looking at negative of log, so it's something like this, okay? So we want to make our x equal to 1. So basically, so that my YC becomes 1 for C equal to 0 and it becomes 0 for our other C's. Is this point clear? Categorical cross entropy loss is clear, right? Okay. Yes.
Can we solve the slope gradient of mean squared error by
By using the good point. Good point. Let me go to another page. Okay, so what is the derivative of, let's say, dou E with respect to dou YC for mean squared error? If, just to remind you, mean squared error is TC minus YC whole square summation over all C, right? So what is my dou E by dou YC? Twice of TC minus YC summation over all C with an into dou YC upon dou YC. Okay, something negative sign, right? Now, what is my dou E cross entropy with respect to YC? What is it? So my E cross entropy is equal to TC log of YC summation over all C. This one is equal to, pardon? Yeah, TC divided by YC into, actually this is C dash if you remember. Yes, just a moment. Let me erase the summation term because we are differentiating with respect to C dash. C dash and then negative sign, fine, minus dou YC dash by dou YC dash. Right? This is TC upon YC, and we know TC is 1, right? Because it is a one hot vector. My TC will be 1 for the, basically delta, this is equal to delta CC dash. Okay, so what is my derivative in this case? So let us assume my YC is very close to 1, right? It is, let's say, 0.7. So what is my, let's remove T because let's say I have 1.2 here. This is just a constant, I can erase it. Okay, what is my YC in this, what is my, this term in this case? This is equal to minus 0.3, right? And what is it in this case? Minus 1 by 0.7, which is equal to minus 10 by 7 is 0.1. Oh, 1.4, I'm sorry. 1.4. So this is how it looks like. It is greater than 1. So the error my error surface is more steep, right? My error surface is more steep. So it pulls very well. Okay, let us consider a case when YC is very close to 0.5. When YC is approximately 0.5. Then what is my dou E MSE with respect to YC dash? Minus 0.5. And what is my dou E MSE with respect to, cross entropy? What is my E cross entropy with respect to dou YC? This is equal to how much? Minus 2. So see, when your error is farther away from the right, when your actual y is far away, it is even steeper, much more than mean squared error. right? So this is the property which is very useful, that when your point is far from the optimal, your error function is very steep, and even if it is close, it is still very steep, very steep. But if you look at the mean squared error, it is a quadratic bowl, right? Okay, 0 here. It is a quadratic bowl, which means that the derivative becomes smaller and smaller, very sharp. It becomes smaller and smaller as it goes closer to 0. On the other hand, my cross entropy function will look something like log, right? Something like this. That you want to reach here, and it's the slope is very sharp. Is this point clear? I think this was not planned, but this just came out in this discussion. That why are we using cross entropy? Okay. Let me ask another question, which is important. Why don't we use single output to represent my classes? Why am I using 3 bulbs? I think you remember the 3 bulb interpretation of this 3 neurons. Why am I using 3 neurons to represent my output? Why not single neuron to represent the output? Yes? Huh? I need 200. 0, 0, 1, and 1, 1, 0. Huh? Oh. That won't matter. So if your y is if you can represent your y, or basically target, you can represent your target as 0, 1, 2, or you can represent your target as what we are doing here, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is called one hot vector. So why not use the first strategy to represent my outputs? Okay, so Ashish's point is that we are making our output as a regression function, but still no problem. No, we can do rounding off. We can round off our values. Pardon?
So in the output, let's say you have 3 neurons. Then at another layer, you only 1 neuron and apply software. You get the output from the system.
That is fine. They are interconvertible, definitely. But why are we using 3 neurons? Or why one hot vector is popular and not the single neuron which represents different classes? So let's say you have C number of classes. You can make you can make a single neuron. It will give values between 0 to C minus 1.
Maybe this is useful in background.
Oh, you can use backdrop there as well. Why not? You're adding a magnitude to a class. Magnitude, okay, no problem. I can normalize it. Divide by 3 or divide by 2, okay. No, there is no magnitude. It's linear scale. Every class is having equal area, I mean the length of the line segment, right?
In the first one, we can pass through one class to the other. So that's the same. In the second one, we are linearly moving towards.
Yes, you are almost there. You're almost there. I think you have hit the point, but in non-technical terms.
So, you're using sigmoid function to derive the activation of each neuron. So, in the first case, it is 0, 1, and 2. The sigmoid function won't reach the activation. But in the second case, the activation.
I can find my separator levels in such a way that the probability of each class is same. I can do that manipulation, but there is some inherent flaw in that representation, in the first representation. So let us say we have roses, and we have lotuses, and we have jasmines, right? And this is my line T, or okay, whatever, Y. So if my Y is 0, 1, 2. What does this mean? This means that my rose is much more similar to lotus than to jasmine. And similarly, my jasmine is much more similar to lotus than to a rose. I'll give you an example. Let us say I find a flower which is red in color, so it is like a rose or a lotus, but its shape is somewhere in between. So your classifier is confused. Classifier says, yes, it is not a jasmine for sure, but it might be a rose or a lotus. So what your classifier will return? Something here, right? Right? But let us say now I have got a small flower which looks something like rose or a jasmine. So my classifier is confused. It might be a rose or it could be a jasmine. So what will be the output? Lotus. So that is an inherent flaw. Okay, let us do the same analysis on the second representation. In this representation, if in the first case, if my flower is something like rose or lotus, what will be the output? What will be the output? 0.5, 0.50, right? And if my flower is something like rose and jasmine, it will be 0.5, 0.5. So this makes much more sense, right? So your space is not giving any preference of distances. Like these two classes are closer, these two are farther apart. This is a serious flaw. That is why we do not use a regression-like approach to do classification. But if you do have this ordering, you can put it in that format. You can make a representation which looks like linear thing, right? Because in regression, you know that your 2 is much more similar to 1 than to 0, right? That is why in regression it makes sense to use a linear scale, but in classification it does not. That is why we don't use. Okay. Next, coming to multi-label classification. What is multi-label classification? Many times it is possible I may have different attributes. I may have different attributes which I want to detect. Let us say face classification. Does a person have beard? Does a person wear glasses? Does a person have hair? Okay. Does a person means I can define different binary attributes. So I may have a beard, or I may not have a beard, or I may have a beard. I may have glasses, or I may not wear glasses. So I may have hair, or I may not have hair. Similarly, mustache or lipstick, or so many things. These attributes I can define. Now I want my classifier, given a face as the input, it has to detect whether those attributes are present or not. This is not a multi-class classification. It is not that if you are wearing glasses you cannot have beard or you cannot have hair, but it is everything is possible, right? So each label can be each label is independent of other labels in general, right? So what is that representation? That representation will look something like this. I represent my output H, which is W times V, previous V, and my labels can go from 0 to L minus 1, and each label can take a binary value. Actually, it can go from 0 to 1. I should have written 0 to 1, which means it could be 0 and it could be 1 too. Ideally, it should be 0 or 1. So this is the thing. And then, how do I define my YL? My YL, my H could be real, right? Because I know it is output of the multiplying a weight vector with my V's, right? Okay, let me write it down to make sure that everybody is following it. Hi2 is equal to Wi2 I1 V I1 summation over all I1, right? This could lie between any minus infinity to plus infinity, but I want to get for each label it should be either 0 or 1 or plus 1 or minus 1. I could use a sign function. If it is a positive value, I make y1. If it is negative value, I make y0. Or I could say sine plus 1 divided by 2. So which means if it is positive, my y is 1. If it is negative, my y is 0. Same thing. Okay, but again, same problem. Now sine is not differentiable, so we need a soft version. What is a soft version? You have already seen that for a sine function, the soft version is sigmoid. So now I can use a sigmoid function, and my y could have values like, let's say my h is something like this. My h vector is, let's say 2.1, 0.8, minus 0.3. So how will the y look like? The y will be like 1 upon 1 plus e to the power minus 2.1, something close to 1, right? Maybe, I'm not sure, maybe 0.8. And this one could be, let's say 0.7 or 6.5, I don't know. And this one will be negative, so let's say less than 0.5, maybe 0.4, right? But the thing is that each output is independent of each other, right? It will not sum to 1 for sure, but its values will be between 0 and 1. That is, it is called a multi-hot vector. Okay, so basically my t is not y, but t is a multi-hot vector. My t could be 1, 1, 1, we have drawn here, 0, 1, 1, 0, 0, 1, anything, 1, 0, 1, 1, 1, 0. Anything is possible. Okay. So now how do I find out my loss function for multi-level classification? So I again go back to probabilistic interpretation. What is the probability of my label being equal to 0? It is YL, because my YL is greater than 0, less than 1. I can use it as a measure of probability. And we have used it in the past. Sigmoidal function has probabilistic interpretation. Then probability of L equal to 1, this is simply 1 minus YL, right? Then binary cross entropy. I use a function. Okay, now how do I compare the two? It is the same thing, cross entropy. So let us say when let's say for beard, my t is equal to 1 and my y is equal to 0.7. Then what will be the binary cross entropy? It will be like probability of The larger the YL, okay, fine. Yeah, you can change it, no problem. It's convention. You can make it 1. Fine, no problem. Okay, so let's say my t is 1 and my y is 0.7. Yeah, I think you're right. If you want to have probabilistic interpretation, then what you're saying is it is correct. So this TL is 1, and what is my YL? YL is 0.7. So log of, basically. Log of 0.7. Let us consider another example. Let's say beard is not there. So T is equal to 0. My Y is equal to still 0.7. What will be my E? It will be 0 into 1 minus 0 times log of 0.3 with a negative sign. Here also negative sign. Okay. So that's the thing, right? And what is the ideal situation when your error will be 0? When your Y is 1 if the T is 1 and Y is 0 when the T is 0. Okay, this is important. Please pay attention here. Error will be equal to 0 when Y equal to 1 for T equal to 1. Basically. And Y equal to 0 for T equal to 0. You can check. Only in that case my error will be 0. So if I am minimizing my error, that is what will happen. Okay. Now coming to the next topic, which is optimization. Let's go through it quickly. How do you optimize your network now? You know you're going to use gradient descent. So you have to find derivative of the error function with respect to the weights, right? So this will be one of the problems in the quiz. Open problem. Oh, not open problem. It's like I've already told the problem which is going to come. So you have to derive the error function with respect to, derivative of error function with respect to the weights, right? It is not straightforward. It means you have to spend some time to be able to do it correctly. Okay. Fine. So in the last class, somebody told about perceptron algorithm. So I thought I will put the reference here. So PRML, Bishop's book, section number 4.1.7, linear classifiers. It discusses the perceptron algorithm, which was very popular. So perceptron algorithm uses a different kind of loss function. The loss function is, because our outputs are +1 or -1, so the loss function is very cleverly designed for that. So please go through this perceptron algorithm, and this is a part of our syllabus. I'm not going through it, but it's a reading assignment for you. Now let's come to optimization schemes. There is a nice lecture slides by Hinton, Jeffrey Hinton, who is kind of father of deep learning, you can say. He's a professor in University of Toronto, and now no more, I think. Now he's in Google. Okay, so, he's still in Toronto. Yeah, he's, I think, so basically he gave these lectures in Coursera, and they became very popular because one of the techniques which he proposed in these lectures, it became very popular for deep learning. So you have a technique called RMS prop, which is very popular for deep learning, but it has no reference. It was never published. It was in the lectures. So that's the another beauty of these lectures. So you can go through these slides as well as the same video lectures here. I have given the reference. Okay, so what is optimization? You have seen that we use gradient descent. So you have something like this. Let's say for mean squared error function, you get a quadratic bowl. So you start from some point here, and then it will gradually descend along the curve, and you will reach the minimum, right? You will reach this minimum point after some time. And then you can have situations like this. where you don't have a circular curves, but very highly oblong or highly elliptical curves. Something like this. That your optimum point is here, but you are sitting somewhere here. Right, the different pen. So this is your optimal point which you want to reach, but currently you are sitting here. So how will the derivative look like? Derivative will look something like this. It won't go towards the center, but it will go in a perpendicular direction. So essentially, if you try to optimize, you will be just oscillating in this direction and very slowly drifting towards the optimal point. But you'll be mostly oscillating and very slowly drifting towards the optimal point. That is why these are the challenges in gradient descent. So what is the remedy? Okay, this is not just the only challenge. You can also have noise. Means this is for E mean squared error, but for a linear neuron. Linear neuron means a linear function, right? But if you have non-linearities, you will get the error function will not be a uniform or elliptical bowl, but it will be very very difficult to navigate kind of terrain, something like this. That's why it is important that how we choose our learning rate. Let us say if I am sitting somewhere here, I go along this direction, I reach somewhere here, and it's almost flat here. I have reached a plateau. A plateau means I am not at the minimum, but it is like the gradients are very shallow there. So what will happen? My algorithm will think I have already reached the maximum or the optimal point, and it will stop. So that is not a good thing. So okay, to take care of some of these problems, there are some heuristic rules which people have come up with. One thing is you move quickly in directions with small but consistent gradients. Let us say we have something like this, a very shallow slope. So what will you do if you are here? Let's say your first step is very small, you come here. Next step is again very small, you come here. Next step is again very small, you come here. But you know that you are consistently descending in the same direction. So why not try bigger steps? So basically you can increase your step size slowly. Make your step size a little bigger. And then you find out, okay, I'm still traveling in the same direction. So why not further accelerate, further speed it up, right? In this way, you can modify your learning rate to go quickly in the right direction. So if you know you're going in the right direction, don't go slow, you can fast. You can make yourself a little faster. Next is move slowly in directions with big but inconsistent gradients. So as you saw in this case. So in this direction, you are moving slow but consistent, right? And in this direction, it is fast because the gradient is very steep, but it is inconsistent, right? As soon as you go there, you have to come back. Again, go in the forward direction, again come back. Fast but inconsistent. Okay, so that's the point. And move slowly in directions with big but inconsistent gradients. So if you know that you are here, then you go there, then you go there, then you go there. You are just moving like this. So why not slow down? Why not go there and reduce your step size so that you come here and then again slow down. And towards the end of learning, reduce the learning rate. Because if you know you're already close to the bottom, and if you still keep oscillating here about the bottom, there is no point in doing that. So reduce your learning rate, make your step size smaller, and you can quickly end up in some small optimal, some good optimal point. Okay, so we'll discuss further in the next class. Thank you.